In this video, we're going to go over the solutions for the 2020 Style FRQ number 1. And this has mixed problems, a lot of Euler's method, tangent line approximations, series convergence, and Taylor polynomials, but it also has some other things thrown in there as well. For this first problem, it's just not an FRQ, it's just a single question, just to kind of get us thinking about how they might ask us an Euler's method problem without being, being just a little bit more conceptual about it, not as direct as we usually have found these to be. Okay, it says let k be a constant and consider this differential equation where y is equal to f of x is the particular solution to the differential equation with initial condition f of 0 is 2 using Euler's method starting at 0 with two steps of equal size. F of 1 is approximately 17/4. What is the value of k? So if you apply Euler's method with two steps of equal size starting at f of 0 is equal to 2, you will get f of 1 is approximately 17/4. So through this process we should be able to find the value of k. Alright, let's start off how we usually would start off. So we start off with our initial point. Here's our initial point. And we usually would be trying to get f of 1. In this case, usually I'll put a question mark there, but in this case they tell us that we get f of 1 is approximately 17/4. This tells us, since we have two steps of equal size going from 0 to 1, delta x here would be 1/2. Okay? And our dy dx is given to us. So let's start off with our first step, dy dx, at our initial point of 0, 2. So 0 in for x, 2 in for y, would be k times 0 squared. So that would be 0. So k times 0 squared plus y is 2. So this would just be a 2. And we would have y minus the y value is equal to the slope times delta x. X minus the x value is delta x. So y would be 2 plus 1, which is 3. So f at 1/2 is approximately equal to 3. That's our first step. Now we go to the second step and we find dy dx at our new point of 1/2, 3. So 1/2 goes in for x. That will give me a k over 4 plus y is 3. So that is my dy dx. Y minus the y value is equal to the slope times x minus the x value, which is my delta x. So y will be 3 plus, I'm going to go ahead and distribute this through, k over 8 plus 3/2. And that is my f of 1, right? So f of 1 is approximately equal to, so 3 plus 3/2, I guess I can go ahead and add that together. This would be 9/2 plus k over 8, and they tell me that that is equal to 17/4. And here's my little equation, and I can go ahead and solve that for k. So I have this equation. I'm going to multiply both sides by 8 to get rid of my fractions there. Multiply both sides by 8. So this will be 4 times 9 plus k is equal to 2 times 17. Oops, is equal to 2 times 17. So k must be -2. So that's one way that they could ask you an Euler's method problem without being super straightforward. Okay? Let's take a look at another way. Number 2 here, consider this differential equation where k is a constant. Let f be the particular solution with initial condition f of 0 is 1. Euler's method starting with two equal steps sizes h is used to approximate f of b. So h is the step size. So after the first step, x is now h, because we're starting at 0. So the first step at x is h, and if you add h to that, you'll get b. So b has to be twice h, right? Okay, so, and we have these answers for those approximations. So we want to find h and we want to find k. All right, so let's start as we always would with any Euler's method problem. We have our initial condition, right? And we have our delta x, which in this case is h. dy dx at our initial point will be k times x, x is just 0, so that's 0, minus y, minus 2 times 0 squared, so that would be a negative 1. So the first slope is negative 1, and then we would write y minus the y value is equal to the slope times our delta x. So y would be 1 minus h, right? So f at our first stopping point of h would be 1 minus h. But we know that that's equal to, it's approximately equal to, but we know that that value is a half, right? From the table, we know that that's 0.5 or a half. So h must be 1 minus a half, which is a half. So h has to be a half. Okay, h is a half. So now we're halfway there. Well, now we need to go find k. dy dx at our new point. Our new point is h 1/2, right? But h is a half, so I'm going to write it like this: 1/2, 1/2. H is a half, and our value is a half. Well, that will equal k times a half, k over 2, minus y, so minus a half, minus 2 times 1/4, right? 2 times 1/4 is 1/2. So that is k over 2 minus 1. So y minus the y value must equal the slope times h, and remember h is a half. Okay, so y would be 1/2 plus, and once again I'm going to distribute that through, so we'll have k over 4 minus 1/2, so that's just k over 4, right? And that will be f of my final spot, b, will be k over 4, but we also know that that is equal to 3. So therefore, k must be 12. So that's a way that they can ask an Euler's method problem that's very, very different from the way that we've been asked them in the past. Let's take a look at number 3. So this, number 3, is a full-blown FRQ problem. Okay, they give us that f is differentiable, f of 0 is 6, f double prime of 0 is a fourth, a portion of the graph of f prime, the derivative of f, is shown. So this is the graph of f prime. And the regions R and S have 1/2 and have areas of 1/2 and 5/8 respectively. So R is a half and S is 5/8, that area, okay? They don't give us the area of Q. Use Euler's method starting at x equals 0 with 4 steps of equal size to approximate f of 2. Okay? So our initial point is f of 0 is 6. We're getting to f of 2, 4 steps, so each step has to be a half. size. So delta x here will be 1/2. Our first slope is when x is 0 and y is 6, so 0, 6. So dy dx is our f prime. That's our graph, right? So f prime, when x is 0, f prime is 1. When x is 0, f prime is 1. So this is just 1 from the graph. Y minus the y value is the slope times delta x. So y will be 6 plus 1/2. 6.5, or I like to write this as an improper fraction. I'm going to write it as 13/2. So our first stopping point, f at 1/2, is approximately 13/2. And now we go to the second step. Dy dx at our new point of 1/2 13/2 will be, so we go to the slope at 1/2. So when x is 1/2, the slope is 2. F prime is 2. Y minus 13/2 is our slope times delta x. So y will be 13/2 plus 1, or 15/2. So our next stopping point, f of 1, is approximately 15/2. And now we go to our next point. Dy dx, when x is 1, dy dx when x is 1 is -2, right? So -2. Y minus 15/2 is equal to -2 times delta x. So y is 15/2 minus 1. We're back to 13/2. And f of 1.5, or 3/2, is approximately 13/2. Last step. Dy dx at our new point, 3/2, 13/2, is when x is 3/2, y, or f prime is 5, right? So y minus the y value is the slope times delta x. So y is 13/2 plus 5/2. So our approximation for f of 2 is 13/2 plus 5/2, which is 18/2, or 9. Okay? Part B, use a tangent line approximation to f of x at x equals 0 to approximate f of 2. So notice that here we approximated f of 2, and here we're going to use a different method to approximate f of 2. Here we used essentially 4 tangent lines to get there. Here we're just going to use 1 tangent line to get there, which should be more accurate. Okay. So if we're using a tangent line, first I'm going to find the equation of the tangent line. The point is 0, 6. We were given that. And the slope, f prime of 0. F prime of 0, remember our f prime of 0 is 1. So our tangent line equation will be y minus the y value is equal to the slope times x minus the x value. That's it. So f of x is approximately 6 plus x. Therefore, f of 2 is approximately 6 plus 2. So using 4 tangent lines, we got 9, and using just 1, we got 8. In part C here, we're going to find the second degree Maclaurin polynomial for f and evaluate p sub 2, the second degree polynomial, at 2. So we're going to be approximating f of 2 again, this time using a Maclaurin polynomial to do it. So here in this problem, I like this problem a lot because we have 3 ways. In each problem, we're approximating the same thing using a different method. Okay, first let's find the second degree Maclaurin polynomial. Maclaurin means just that it's centered at 0, right? Centered at 0. So I'm starting with f of 0, and f of 0 was given to us to be 6. F prime of 0, we can get from the table, f prime of 0 is our 1 that we've used in all 3 parts so far. And f double prime of 0 was given to us. I remember reading that in the problem. F double prime of 0 is a 4th. So they just gave us that. So the second degree Maclaurin polynomial will be 6 plus 1 over 1 factorial x minus 0 to the first power plus 1/4 divided by 2 factorial times x minus 0 squared. That's the second degree Taylor. And if we want to evaluate, or we want to approximate f of 2 by using this polynomial, we need to put 2 in for x. And if we do that, this is just going to be a 2. And this will be 2 squared over 4, right? So that cancels, and I just am left with the 1/2. So this turned out to be 8.5. Look how close these were to each other, these 3 approximations. Okay? All right, part D. If the integral from 0 to 1.5 of f prime, that's the area under our curve of f prime, or our area, if that is equal to this summation, find the integral from 0 to a of f prime. Well, let's take a look at this, because this summation, I recognize this is a geometric series with r negative 7/9. And so I know that I can find that sum because this is a converging geometric series. That's one of the few that we have this short little formula to find that sum. So let's write that down. So this series is geometric. R is negative 7/9. And a, the first value, when we put 0 in for n, this is going to be 1 times 2 is just 2. So the first term is just 2. So the sum will be a over 1 minus r, right? Since I'm going to be using this, I'm going to go ahead and, I could just leave it like that, but since I'm going to be using it, I'm going to go ahead and simplify this. I'm going to multiply top and bottom by 9. We get 18 over 9 plus 7, which is 18 over 16, or 9/8. So I feel confident in that, but if I didn't feel confident in that, I would just leave it like this. That's fine. So we know that this integral, that integral is equal to 9/8. Okay, so that is the integral from 0 to 1.5. 0 to 1.5. So we know that that entire integral is 9/8. I know this area, and I know this area, so now I can find the area of Q here, the area of region Q. And that is what I'm trying to find in this problem, because we're asked to find the integral from 0 to a of f prime, and the integral from 0 to a is that area of Q. So the integral from 0 to 1.5, this is the entire thing, that is equal to Q minus r plus s, right? So I'm going to write that as the integral from 0 to a of 1.5 of f of x dx plus the integral from a to this is going to be 1. Well, you know, I'm just going to say the area from a to 1.5. I can do that. To 1.5 of f prime of x dx. Okay. So that tells me if so I'm going to just subtract, this is what I know, right? That's just negative r plus s. So this I'm going to take to the other side, and this is my 9/8. So 9/8 that I just found is equal to, let me write this out again, the integral from a to 1.5, that's negative 1/2 plus 5/8, right? So minus 1/2 plus 5/8. So therefore the integral from 0 to a of f prime of x dx will be 9/8 plus 1/2 minus 5/8. And I would just say stop there. If you can't stand it, that is equal to 1. Okay, lastly on this problem, it says the average value of f prime over the interval from 0 to 6 is 1/2. Find the exact value of f of 6. So they're telling us that the average value of f prime on that interval is 1/2. Let's set up that expression, that equation. So the average value of f prime on that interval is 1 over 6 minus 0. We should know our formula for average value of any function. Remember, we're finding the average value of this function, so that's what needs to go in here. And we know that that is 1/2. If I multiply both sides by 6, I get that integral is equal to 3. And when I see integral of f prime, I know I can just use the first fundamental theorem. Integral of f prime is just f, and we're going to evaluate that from 0 to 6, so that's f of 6 minus f of 0, and that's equal to 3. We know f of 0 is 6. That was one of our pieces of information we've been using throughout this problem. So f of 6 must be 9. So this answer kind of just fell into our laps when we analyzed what this meant. So nice little problem. I like that problem. Euler's method, tangent line, Maclaurin, series, a converging series, average value, and plain old fundamental theorem of calculus. So nice little. Okay, let's take a look at number 4 here. And number 4, it's just 2 problems, but they're both good problems here. And it presents things in a little bit of a different way. It says let y equals f of x be the particular solution to this differential equation with initial condition f of 3 is -7, where a portion of h of x is given in the figure above. So I see that h of x, they didn't tell us that this was piecewise linear, but I'm going to assume that it's piecewise linear. In a like a real AP question, they would definitely tell you that, but we're going to make that assumption here. First of all, in part A, use Euler's method starting at x equals 3 with 3 equal steps to approximate f of 0. Okay, if we're starting at x of 3 and going to 0 with 3 steps of equal sizes, I know delta x will be a -1. We're going backwards to -1. Okay, so our first slope, dy dx, we're starting at when x is 3, so 3 -7 is going to be x h of x, so that will be 3h of 3. H of 3 from our graph, h of 3 is a -1. So dy dx, our first slope, is -3. Y minus the y value, the y value is -7, so we'll have a y plus 7 here, is equal to the slope times delta x. So y will be -7 plus 3, which is -4. So our first stopping point, f at, so we started at x equals 3, we went down 1, so we're at x is equal to 2. F of 2 is approximately -4. On to our second step. Dy dx at our next point, 2, -4 is equal to, okay, x is 2, and we multiply that by h of 2, right? Well, h of 2 is 2, h of 2 is 2, so this slope will be 4. Y minus the y value is equal to our slope times delta x. So y will be -4 minus 4, which is -8. And so our next stopping point, we started at 0, we started at 3, then went down to 2, now we're going down to 1. And that value is approximately -8. Third and final step, dy dx at this point will be 1, h of 1. H of 1 is 1 from our graph, so this is just 1. Y minus our y value is equal to our slope times delta x. So y is -8 minus 1, which is -9. So f at 0 is approximately -9. Okay, part B. The function g has derivatives of all orders at x equals -2. Let t sub n denote the nth degree Taylor polynomial for g about x equals -2. The nth derivative of g at x equals -2 is given by this formula. For n is greater than or equal to 0. So even at the 0th derivative, which is just the function, this formula will work. And we need to find the third degree Taylor polynomial. So we start with g of -2. Always start with g, your function at your center value. And remember, this formula in this case will work even for the 0 derivative, which is just our function value. So we'll have -1 to the 0 divided by h of 0. -1 to the 0 is just 1. H of 0 is 1. So g of -2 is just 1. Now we go to g prime of -2. So g prime of -2, now n will be 1 because we're in the first derivative. So this will be -1 to the first, or just -1, h of 1. So -1 over, and then h of 1 is from the graph, we know h of 1 is 1. So g prime of -2 is -1. On to the second derivative, n will be 2. So -1 squared is just 1 over h of 2. H of 2 from the graph, h of 2 is 2. So we just have 1 over 2. And the third derivative, we need to go to the third derivative because we need that third degree Taylor. This will be -1 cubed, which is -1 over h of 3. H of 3 is -1. So the third derivative at -2 is 1. Okay, so they tell me to name it t sub 3. The third degree Taylor at x will be, okay, we start with our our function value of 1, and then we immediately go to our first derivative. The first derivative is 1. That'll be 1 over 1 factorial x minus our center. The center is a negative 2, so this will be minus a negative 2, or plus 2 to the first power. Then we go to our second derivative. Our second derivative is 1/2. We divide by 2 factorial, and then x minus a negative 2 again, squared. And then we go to the third derivative, 1, divide by 3 factorial, x minus a negative 2 cubed. And that is t sub 3 of x. That would be our safe stop spot. So, not a bad little problem. I like that we got to do a Taylor polynomial in there and an Euler's method problem in there. Next up, let's take a look at number 5. This is a 3-part question. Number 5 is. It says, consider the function a sub n is negative 1 to the n over n, where n is a positive integer. I kind of recognize that. Hopefully you do too. That's our alternating harmonic series. If this was a series, it would be our alternating harmonic series. Maybe that'll come into play here because that's one of the things that was on our list that was included in this year's exam. Let y equals f of x be the particular solution to this differential equation with initial condition 1, 5. So f at 1 is equal to 5. Okay? For positive integer values of x, f prime of x is equal to a of x. Well, that's interesting. So f prime of x, for positive integer values, f prime of x is equal to negative 1 to the x over x. Okay. Part A. Use Euler's method starting at x equals 1 with 3 steps to approximate f of 4. So we're starting at x equals 1, we're going to x equals 4, so delta x will be a positive 1 because we're using 3 equal steps. So dy dx at our starting point, x is 1, y is 5, will be, okay, so I should have written that down. Oh, x. Negative 1 to the x over x, right? So we'll have negative 1 to the 1. That'll be a negative 1 over 1. So negative 1. Y minus the y value is the slope times delta x. Y is 5 minus 1, which is 4. So our first stopping point, we started at 1, we went up 1, so we're now at 2. Our first stopping point, f of 2, is approximately 4. Second step. Okay. Putting 2 in for x, we'll have negative 1 squared, which is 1 over 2. So y minus the y value is our slope times delta x. Y is equal to 4 plus 1/2. I'm going to write that as an improper fraction. This will be 9/2. So f at 3 is approximately 9/2. Last step, dy dx at our point 3 9/2 is going to equal negative 1 cubed is negative 1 over 3. Y minus the y value is equal to the slope times the delta x. So y is equal to 9/2 minus 1/3, and f of 4 is approximately 9/2 minus 1/3. And I would definitely just leave it like that. Okay? Not bad. All right. Part B. Let E sub c be the approximation for f of c found by using Euler's method starting at x equals 1 with step sizes of 1 where c is a positive integer greater than 1. Okay, that's very wordy. You may need to read that twice. Determine if the limit as c goes to infinity of f of c converges or diverges, and give a reason for your answer. Let's take this apart. Okay, I want to find out. I know I want c to go to infinity, but let's just find some values for this e sub c thing going on. Okay, I know that it was the approximation for f of c found by using Euler's method, but c is going to vary, right? So let's see. From up here, if we just did a single, for e sub 2 here, that would be our e sub 1 would just be our function value. So e sub 2 would be just this first stopping point. That would just be our first stopping point. Okay, that would be a step size. That would just be a one-time step. That would be a one step, right? So this would be 5 minus 1, which was 4, right? For the next step, if we want one more step, we would take that 5 minus 1, and then we would add a half to it, right? So we'd have 5 minus 1 plus 1/2. And I said this is equal to 4, and it is, but I'm just going to leave it like that. See if we can see what's happening here. For e sub 4, we took this value, the 5 minus 1 plus 1/2, and what did we do with that value? We subtracted 1/3 from it, right? Take a look at what we have here. What would the next one be? E sub 5 would be 5 minus 1 plus 1/2 minus 1/3. What's the pattern? Plus 1/4. That's what would happen, right? So if we keep on going in this pattern, e sub c, for c greater than 5, would be 5. And then for this, I'm going to write this as a series, okay? Since I'm starting with negative, I'm going to make this plus, and then I want my first term to be negative, okay? I'm going to go to c here, and my first term is going to be a negative, so I'm going to make that just an n here over n. Okay? So we're asked to find the limit as c goes to infinity of that e sub c, and that will be the limit as c goes to infinity of 5 plus that series, right? So the question is, does this converge or diverge? Does this converge or diverge? Well, the 5 plus won't affect the convergence or divergence. And so the question is, does this converge or diverge? Well, that is our alternating harmonic series, which we know converges. It converges conditionally, right? So this converges since that series is the alternating harmonic series. You could also say it converges by p-series, alternating series test. Sorry, alternating series test. It's not p-series. Okay? All right, let's take a look. In part C, it says, let S be the series defined by this, where P is a real number. For what values of P does S converge? Okay, so S is equal to the series. It's the absolute value of A sub n, and A sub n is equal to this. And they tell us this is to the 5 minus p squared power. Okay, the absolute value will make this always positive, right? So we have 1 over n, and that power will apply to the 1 and to the n. N to that power is just 1. So this is 5 minus p squared here. And all of a sudden now I see this p series. And I know the p-series, this power, for this to converge, this power has to be greater than 1. We know that about a p-series. So this converges when 5 minus p squared is greater than 1. And now all we have to do is solve that. So p squared, if we take that to the other side, p squared will be less than 5, right? And so, oh, I'm so sorry, not greater than 0, greater than 1. I'm so sorry. So that's a 4 there. A p-series converges when that power is greater than 1. I don't know if I said that right when I was talking, that it converges, this power has to be greater than 1, not 0. Okay, so we get this expression, so p squared is less than 4. And that means that p has to be between -2 and 2, solving that little inequality. Okay? The last problem on this in this little packet for this first mixed FRQ worksheet is number 6. We have a function g, and it has derivatives of all orders at x equals 1, and the second degree Taylor polynomial for g centered at x equals 1 is given by this. So they give us the second degree Taylor polynomial. From this we could get g at 1 is 4. We know that g at 1 is 4. And we could get g prime at 1. It's not equal, well, actually it is equal g prime of 1, since this -2/3 is g prime at 1 divided by 1 factorial, right? So g prime at 1 has to just be -2/3, right? 5/2 is equal to g double prime at 1 over 2 factorial, right? So therefore g prime at 1 has to be just 5. So I don't know if we're going to need that. I'm thinking we might need that. But anyway. All right. Part A. Let t sub 3 be the third degree Taylor polynomial for g centered at 1. And if t sub 3 at 2 is 3, find g triple prime at 1. Okay, so first I'm going to write a general form for t sub 3, the third degree Taylor. I'm going to use the 4 minus 2/3 x minus 1 plus 5/2 x minus 1 squared. That would be the second degree. For the third degree, I need to add one more term, right? It will be g triple prime at 1 over 3 factorial times x minus 1 cubed. That's what that will be. They tell me what happens if they put 2 in for x. If we put 2 in for x, we get 3 for that value. So this would be 4 minus, if I put 2 in for x, each of these parentheses will be just a 1, right? So this will be just 2/3, negative 2/3, plus 5/2 plus g triple prime at 1 over 3 factorial, and that will equal 3. Okay? So g triple prime at 1 over 3 factorial will equal 3 minus 4 plus 2/3 minus 5/2, and so g triple prime at 1 would be 3 factorial, which is 6, times 3 minus 4 plus 2/3 minus 5/2, and that would be my safe stop spot, and I'm good with that. Okay? Unless I need to simplify it, I'm just going to leave it like that. Okay, part B. Let y equals f of x be the particular solution to this differential equation. So know that since this is in parentheses, they're talking about a derivative here. This is the 2x minus 4 derivative of g at 1, where the nth derivative of g at 1 is the nth derivative of g at 1. Okay, gotcha. Okay, it's what I said 3 times. All right. F of 3 is 8. Use Euler's method starting at x equals 3 with 2 equal step sizes to approximate f of 2. Okay? We're starting at x equals 3 and we're going to x equals 2. So delta x will be a negative 1/2 since we're using 2 step sizes, 2 equal steps. Okay? All right, dy dx. At my starting point is 3, 8. Okay? Is equal to, here's my formula for dy dx. Well, it's what derivative? It's when x is 3 here, so this would be 6 minus 4, so it's the second derivative of g at 1. So dy dx is the second derivative of g at 1. This is g double prime at 1. Okay, and g double prime at 1 was what we found way up at the start when we were just kind of playing around on what we could get from this. G double prime of 1 is 5. So this first step is that slope is 5. Y minus the y value is the slope times delta x. So y will be 8 minus 5/2. Okay? And 8 minus 5/2, 8 is 16/2, and 16/2 minus 5/2 is 11/2. So our first stopping point, we started at 3, we're heading to 2, we're halfway there, so we're at 5/2. F at 5/2 is approximately 11/2. On to our second step. Dy dx at 5/2, 11/2 is equal to, okay, if I put 5/2 in for x, this will be 5 minus 4, or 1. So it's the first derivative at 1. So it's g prime at 1. Again, we found that up here. G prime at 1 is negative 2/3. Y minus the y value is the slope times delta x. So y is equal to 11/2 plus 1/3. And f of 2 is approximately 11/2 plus 1/3. And I would say stop there. Okay, good little problems. Great review for all the Taylor polynomials and Euler's and a variety of some other things as well. So nice little review packet.